Today we're going to be talking about writing inverse equations of exponential and logarithmic functions. And we've kind of talked about this before, but we're saying that the definition of a logarithm it follows that the logarithmic function g of x equals log base b of x is the inverse of the exponential function f of x equals b to the x power. So it just means they're interchangeable. And, we talked about this yesterday where whenever you get, we haven't talked about this part yet, but if you do a composition of functions, g of f of x here, which means you take the f function and you input it into the g function, this is what we talked about in mod 1, you're going to get this, log base b of b to the x. And what that means is the next step you could do is drop the x out front, and you get x times log base b of b, and we know log base b of b is just 1, and that gets us to x. Likewise, if you do the opposite function, f of g of x, you're going to get the inverse. You're going to get, this log base b, or b to the log base b of x. And we talked about this yesterday. This is what we specifically talked about yesterday. Was technically you can drop the x out front and you're going to be left with b times log base b, which is kind of weird, but that's just a 1. And then you'd be left with x. And we know that when you do a composition of two different functions and you get e equals x, that's the definition of an inverse. So that's how we know exponential functions and logarithmic functions are inverses of each other. And that's, again, why logarithms were invented in the first place, because mathematicians had exponents and they said, how do we create an inverse for this type of function? And that's where logarithms came from. Okay. So for these first two problems, we want to simplify each expression. So I'll show you a couple examples here. So the first one shows me like 10 to the log of 4 power. And there's no base written, so that's technically going to be a base 10. So what you could do is you could move the 4 out front and say you have 10 to the log base 10 power. It's just not written. So it would just simplify to 4. Okay, that would be our first example. Second example is going to be a little bit tougher when we're simplifying. First things first, I've got log base 5 of 25 to the x. I can move the x out front. That's the property of logarithm. That's fine. And then I have log base 5 of 25. Now, there's a couple ways I could do this. One way I haven't shown you guys yet that you could do this is thinking about 25 here. Want to say, how can I rewrite 25 in terms of 5? And I mean, in general, in terms of the base. How can I get 25 to be a 5? That's like in another way to put it, I guess. And what I mean by that is you can think about 25 is the same as 5 squared. So I could do a little substitution here and say x equals log base 5 of 5 squared. And that means when I have 5 squared, I can, take that 2 and drop it out front. And I get 2x equals log base 5 of 5. And log base 5 of 5 is just 1, so I get 2x times 1, or just more simply 2x. And that would be the simplified expression there. So we haven't specifically talked about replacing the 25 with the 5 squared. What we've talked about in class more so up to this point has been more just, I can say 5 to the question mark equals 25. So let's figure out what the question mark's going to be. And we can say, oh, 5 to the first is 5. 5 squared is 25. So that means question mark's going to equal 2. And then I can substitute a 2 in there for log base 5 at 25. So we've talked about that, but this is just another way to look at it. And maybe this makes a little more sense to you. If this is more confusing to you and you like the method that we've been working on up until this point, like doing this method instead, that's perfectly fine. I'm just trying to show people another way how to look at these types of problems. So if what I'm showing you right now doesn't make sense and you like the other method, please stick to the other method. But if this one's like, oh, okay, that makes a little more sense, great. So it's whatever works best for you, okay? That's really the goal that I'm trying to get at right here. I'm just showing you another way to think about the same type of problem. All right, just trying to reach the most students as possible. And I might just be confusing you further if you're already confused. And if that's the case, then please let me know that, and we can meet after class and work on stuff some more and just get more practice. All right, the next thing I want to do is I want to just find the inverse of each function. And we haven't explicitly done this yet, but we should know how to do this by now. Just a reminder that when you find the inverse, the first thing you're going to do is swap x and y, just like we did in mod 1, x equals 6 to the y. And then we're going to solve for y. And there's a couple ways we can do this now, since we've talked about it a few times. Let's do method 1. We're going to do the change forms method. Change forms, we know that the base of the exponent becomes the base of the logarithm, and logarithms solve for exponents. There's our change forms method. All right, so if you like changing forms, awesome, use that method. The other method we talked about was a little more algebraic, and we said that's like the log both sides method. And when I log both sides, I want to choose base 6 specifically, because this is already a base 6 here. So I can write this as log base 6 of x equals log base 6 of 6 to the y power. And this is another method that algebraically might make more sense to you than the changing forms and memorizing how to change the forms. Because now I have this y exponent that can drop out front, and I have log base 6 of x equals y times log base 6 of 6. And we know log base 6 of 6 is 1. So we end up with y equals log base 6 of x. So either method, method 1 or method 2, is going to get you to the same result. But that's the idea for writing inverses of these functions. Okay? And all of mod 2, all of mod 1 was kind of building to this. All of mod 2 was kind of building to this. Now we're at that point. Now we can write inverses of these logarithmic functions. We can do that to solve these equations. We've been doing all of this, all right? So this is just kind of putting it all together up until this point. All right. One more example here, and then I'm going to let you guys do a little bit of practice. Y equals natural log of x plus 3. Let's do this one in purple. So first, switch x and y. X equals natural log of y plus 3. I have the logarithm isolated on one side of the equation, so I can go ahead and change forms, or I can take a base of both sides. In this case, I'll just show you the base e of both sides method. And I'm choosing base e because a natural log is a log base e. So I get e to the x equals y plus 3 times e to the natural log, which this is just going to become a 1 right here. So I end up with e to the x equals y plus 3. And then finally, to get y by itself, I'm going to subtract 3 from both sides. E to the x minus 3 equals y. And there's my inverse of this particular function. Yes.
Yeah, sorry. I was wrapping up the other example. Where did the e come from?
Oh, because natural log is log base e. So when I'm changing forms, I want to use base e to get rid of that natural log.
Okay, so pretty much, so you get rid of the natural log, and in its place is e.
Yeah.
Okay, cool.
Okay. Okay. So then now I've got 6 problems I want you guys to try. The first 4 are simplifying, just like our first 2 examples. And then 5 and 6 are going to be find the inverse of each one. So I want you guys to practice a little bit here. Let me know if you have any questions at all. I'll try these 6 out. I wrote down all the answers for these ones. If you have any questions, any of those that you want to look over a little bit more, please let me know, and we'll take a little bit more in-depth look at them. But like for now, I just wrote down the answers for time-saving purposes. But if you want to see them worked out, let me know. Which ones?
Yeah. So I've got a question.
Okay. Yeah.
When you move the exponent to the front, is it the whole exponent or just like the very end of the exponent?
It should be the whole exponent. So for like example number 2, the whole exponent is negative 3x. So that's the whole exponent because it's 7 to the negative 3x power. So we move that whole thing to the front.
Right.
All right.
But like for number 1, would you move all of log 8x?
So this one, you can only move an exponent to the front if it's like a log based something. So there's no log in front here. So in this case, what you do is you just move the x to the front, and it's just because you have the 8 log base 8 in a row, and then 8 log base 8 is the 1. So yeah, that one's a little trickier. That one you just kind of have to recognize what's going on with it. That's going to be the same thing with number 4, where it's e log base e is another way to look at that one. It's like e log base e of 20.
So the e and the log both cancel out there, right?
Yeah.
Not the log, the e and the ln.
Yes.
Both natural log. And then for number 5, I might have done this wrong, but I thought I got log base 4 of y equals x.
Okay. For which one?
For number 5.
Okay. So yeah, first step is you switch x and y. So you should write it as x equals 4 to the y power. And then we change forms. And logarithms always solve for exponents. Since y was the exponent, it should be on the other side of the equal sign after we switch forms. Okay? So that's the idea for that particular problem. Okay, so now the next set of examples I want to show you, these inverses get a little bit trickier when we're writing them. And the key for these 2 problems is we have 2 to the x plus 1 power, or we have log base 5, the logarithm, or the base 2. Those are not isolated at the beginning of the problem. So first thing we do, same idea, switch x and y. But then because they're not isolated, I have to get rid of that 5. So I have to add 5 to both sides. X plus 5 equals 2 to the y plus 1. Same thing over here on the second problem. After I switch the x and y, I have to get rid of that 3, so I have to subtract 3 from both sides. X minus 3 equals log base 5 of y minus 2. So now I have x plus 5 equals 2 to the y plus 1. X minus 3 equals log base 5 of y minus 2. So now what happens is I can change forms and say, okay, base 2 becomes my base of my logarithm. And I'm solving for the exponent. The exponent in this case is y plus 1. On the other one, the exponent is x minus 3. So that becomes 5 to the x minus 3 power equals y minus 2. So these ones are a little bit trickier because we got to do a step before we can start changing forms. And then now we have this y plus 1. I still have to get y by itself here. So I'm going to subtract 1 from both sides. And then over here to get y by itself, I have to add 2 to both sides. All right, so it's still 5 to the x minus 3 power plus 2. One way you can double check these answers, again, open notes on assessments. You can always refer back to my notes, but you can go to Desmos and graph these. Graph the original function, graph the inverse. Make sure that you can find that vertical asymptote and that the horizontal asymptote is the exact same value. So if it was x equals 2 for the vertical asymptote, the horizontal asymptote should be y equals 2. If it's not, that means I did something wrong in my calculations. I can tell right there that something's not quite right. So it's a good way to always double check your answers is look at the graph and see what the graph's telling you. Okay, I'm going to do one more round of examples here with kind of our toughest problems at the end. We're just going to do some solving. But I want you to try these 4 problems that are slightly more difficult. Hint on number 3, because you have 2 logarithms on one side, you might want to condense that to a single logarithm before you change forms. That's your hint for number 3. Try these problems out now. So last thing today is solving these equations. And I just have 3 quick examples to show you again for solving, which is what we worked on yesterday as well. So what you could do is you have log base 2 of 4x. It's a single logarithm. You can go ahead and write this as like you do base 2 to both sides if you want. And you're going to get 2 log base 2 of 4x equals 2 to the 12th. Or you can just change forms, whatever works easier for you. But we're going to get 4x equals 2 to the 12th power. 2 to the 12th power is going to give us a big number. All right. 4,096 big. Then we divide both sides by 4. X equals 1,024. You'll want to check for an extraneous solution because this was a logarithmic function. But the nice thing for these problems is this logarithm, I can tell because it's just a 4x, the domain would have started at 0 and gone to positive infinity. So 1,024 should definitely work when we double check that. But it's always good to check just to make sure you did your math right as well. Example B, 5 to the x equals 120. Let's take log base 5 of both sides. And we can drop the x out front. And then we have x times log base 5 of 5. That's a 1. So we get x equals log base 5 of 120. I can change forms to put that in my calculator. If I have the calculator that lets me just put it in my calculator directly, I can do that. I'm going to change forms since I don't have that calculator on me right now. I actually don't even own a calculator that does that. I always do change a base formula for these problems. And I can go ahead and do the log of 120 divided by log of 5. And I get x is approximately 2.97 rounded to the nearest hundredth. And then example C, the last problem here, 2 logarithms. This is where I'd want to condense them to a single logarithm. I can say log base 2 of 5 times x plus 2 equals 4. Multiply both sides by 5, or distribute that 5, I should say, and I get 5x plus 10 equals 4. Now I can do a base 2 of both sides. And I end up getting 5x plus 10 equals 2 to the 4th. 5x plus 10 equals 16. Subtract 10 from both sides, 5x equals 6. Finally divide both sides by 5 and I get x equals 6/5. Okay, that's the idea with those last 3 examples there. Okay, now I have 3 for you guys to practice again. If you're feeling okay on those, you can jump into the assignment if you want. I'll hang out obviously until the end of class at the very least to answer questions and everything like that. And I will put these answers up in just a second for these last 3 problems. But I'm going to give you time to work on these 3, or feel free to get started on the assignment if you're feeling comfortable with these 3. All right. Also, if you have any questions on the homework assignment, feel free to let me know. If you want to work on the assignment with me, feel free to stay online. If you're done, have a great day, and we'll see you guys on Thursday. Don't forget about the graded assignment tomorrow. Thanks so much, guys.